Good morning, everyone, and thanks so much for the invitation to chat to you this morning. It's quite an honor to be surrounded by so many systems engineers. I have to say it's one of the slickest conferences I think I've ever attended. So it's congratulations on a well-organized event. I would expect nothing less from so many system engineers. I hope you can all understand what I'm saying. I hope my accent isn't too strong for you. If it is, you're going to have trouble in Edinburgh next year. And I suggest you brush up on your Polish in that case. I've attended a few of the presentations so far, and I found them very interesting, particularly the plenary sessions. It's very hard to follow such slick presentations. I think all of you have been taking away various things from the different presentations. Before I start mine, I'd just like to mention a couple of the things that I noted. Yes, in day one, I think it was Chancellor Kateni from Davis University. She mentioned she's got a $4 billion budget. If I read the slide, I think that's what she said in the slide. I mean, that's more than most small countries. The other thing I picked up from her presentation, animal rights have more rights than humans in America. I think that's a great thing. And I think the third one, it was a word, phenomenological. Phenomenological. I'm going to take that word back with me to South Africa and use it in my next presentation there. Yesterday, Jan Bosch, he did a great presentation about Sweden and such like. He was mentioning software companies. If you're not part of a software company, you won't have a job in 10 years' time. That's quite frightening for me, particularly. What other thing? Yeah, 7% of functionality is used in software. That's also quite good. I quite like that point. That's a very valid point. And I think the third one, yeah, if you're looking for a new car, you should buy the XC90 Volvo. So, okay. To start off, coming on to what I'm supposed to be talking about, I was looking for a quote. I noticed everyone likes to use quotes. Let me just get this started, actually. There we go. Everyone likes to use quotes, so I've been looking for a suitable quote to introduce my South African presentation to you. And I had a look at some Churchill and various presidents of the United States. The one that most suited the one that I felt was more appropriate to my presentation was this one by Cap Spock of the Starship Enterprise. It's life, Jim, but not as we know it. So I'm going to, on that, the one takeaway point that you should take away from this presentation today is South Africa is not the whole continent of Africa. It's the wee bit at the bottom here. Okay, it's just that little bit there. So it's right there. The reason I say that is I was looking at the news, and one of your news readers was talking about the abysmal situation in Zimbabwe, which is a country up here, and she said in Zimbabwe in South Africa. She introduced Zimbabwe as being part of South Africa. It's a different country. Don't confuse the two. Okay. So that's the takeaway point. You can now relax and we'll carry on. I'm going to start with a bit of an introduction just to show you a few scenes from South Africa, just so that you can get the idea. It's not such a bad place as everyone makes out. It's actually quite nice. It's got nice hotels, nice mountains, nice seaside hotels. We've got the Big Five. You've all heard of the Big Five. We've got the elephant. We've got the leopard. Leopards are good. We use them as security guards on some of our installations. Rhinoceros, yep, the rhinos. Then we've got the buffalo, the African buffalo. And then, of course, the lion. Everyone likes the lions. They're playful things. Inquisitive. They like, so you've got to, it's friendly. They like visitors. Obviously, with austerity measures kicking in all over the world just now, not everyone has access to dollars. I realize that most of the Americans will go to the big game parks and see the big five, but if you're a bit short on cash or you're a bit tight with your money, then you can go and see the little five, where you can basically just drive about and pick them up as you go along. That's one of them. This would be another one. It's mainly Scottish people that go on this tour, and a few Greeks now. This is one of my friends from the International Water Association, Stuart Hamilton with 4 penguins. Stuart's the one on the right there. And we've got a competition. Everyone's alike to competitions, so I've decided we'll have a competition as well. And let's get this going. Have a bit of a competition. This is a dassy, or rock hyrax. It's called a rock hyrax. This is one of the little five. The competition is only open to people that are not South African and were not born in South Africa, okay? And there is a prize that you can get if you come up at the back. If you've got your cell phones ready, don't worry, because we're doing this a different way. You're going to shout out the answer, okay? The question, which animal in Africa is the closest living relative to the rock hyrax? Elephant. Who said elephant? Okay, you can come up at the back. Thank you. You've won. Well done. I'll check your passport. If you just bring your passport up at the end. I have a prize for you, which you can collect at the end. I've got it right here. It's very, very valuable. Okay, South Africa, some slides. Let me just see where this, there we go. South Africa basically is a country of extremes. We have some very dry, arid areas moving into some wetter, more temperate type climates. And we also have extreme drought events. And I'm going to touch on a few hydrological issues and some system modeling issues. We often have drought events moving up to 10, 15 years. And it's quite a challenge in order to plan for these events, because you're never quite sure when you're moving into a drought. It's always easy to look back and say it started 2 or 3 years ago, but you're never quite sure when it starts. And they normally come and bite you when you're least expecting it. This slide here is, just to give you an indication, the top bar, the top of the bar represents the total storage of the dams in South Africa. You don't need to worry about the units. All we're looking at here is the blue bar represents the total volume of water in the dams at any one time. So the yellowy orange pieces represent empty storage in the dams. So if the dams are low, or the reservoirs are low, we'll have, they'll be down here. So this would be a drought, this would be a drought, that would be a drought. You can see that we had a drought back in about 69, back there. We had a bad drought back here in 1983. We had a drought in 1993. We had a drought in 2003. And for the past 10, 12 years, our dams have been spilling. So we haven't had a drought now for about 12, 13, even 14 years. We're well overdue the next drought. And unfortunately, people have short memories, and most of the people in South Africa just now are wasting water significantly. But the next drought is coming. And this is just one of the things that you have to this is not climate change. This is just natural drought events. What happened in 1983? The country was in the grips of the worst drought on record. And the government decided to develop system models in order to manage the country's water resources. So they came to America and Canada, and they basically selected a model which was a Canadian model originally designed for hydropower optimization. And they pulled in some experts from America, Prof. Laux from Cornell University, Prof. Stedinger, Professor Grieg, Colorado. There were 3 software engineers. It was myself, Rick Allen, and Peter van Rooyen. We were using Fortran. I don't know if any of you remember Fortran. If anyone needs a good Fortran programmer, you can come and speak to me afterwards. There doesn't seem to be a great call for them these days, but anyway. And we had a professor from the University of Natal, Prof. Pegram, who developed the stochastic models, which I'll come on to a bit later. The algorithms that were used were developed by a guy by the name of Oscar Sigvaldason, and they were developed originally for optimizing hydropower within the Canadian power network. The models had no stochastic capabilities. I'll explain that a little bit later on. When I mean stochastics, I mean that we generate synthetic streamflow sequences which are similar to what happened in real life, but a different sequence of events. And by running stochastic sequences, you can get an idea of the risk of failure, etc. So basically, we'll come on to that. This was our first computer that we used. It was imported from the States, as you can probably gather, back in 1983. This was during the apartheid years, and America was very kind to give South Africa, or sell South Africa, one of these large computers, which we used to run the system model. The biggest problem with this computer was the fact that it needed an air conditioning unit to keep it cool. And it was forever breaking down. And as soon as the air conditioning unit broke down, then these disk drives there basically hemorrhaged, and the whole thing fell apart. So we were forever having to repair it. So we got a small one, a little Microvax, back in 1987, which was a big improvement. We didn't need a team of 12 people plus an air conditioning company working for us. We analyzed the first big system in 1985, and then in 1987, we modeled the Orange River system, which I'll show you shortly is one of the biggest in South Africa. And we also did the Namibian area, where we incorporated deep groundwater aquifers in the model as well. Creating a system model, you start with a map of the area, your demand centers, your rivers, your reservoirs, etc. You create a stick model. A reservoir is a triangle. Any channel is just a little link. You can have hydrology coming in, demand centers, irrigation demands, town demands, whatever you want. So you set up a system model like that. You then add penalty structures, which is basically how the model operates. It's a penalty structure-driven model, which I'll talk about in a little bit. At this point, you still have reservoirs and channels involved. But the final step in actually analyzing the model is we convert the reservoir channels, or the reservoirs, to channels depending on the storages within the reservoir. And we end up with a network model that can be solved by a standard linear programming solver. And in our case, we used the out-of-kilter solver, which is one of the most solid and robust solvers that we could actually work with. It worked very well, and it's worked for the last 30 years now. The model that I'm talking about today is this is the Orange River Basin. This is South Africa again. This is the Orange River Basin. We have 1, 2, 3, 4, 5, 6 adjacent river basins which are linked to the main river basin, either by pumping water over 1,500 meters of mountain or taking it through with a tunnel. We've got a couple of tunnels going through 80-kilometer tunnels connecting some of the catchments. Just to put it in perspective, this is Washington State here. So you can see it's a fairly reasonably big river basin. I know in America you like big things, so I thought this is a big river basin. It has lots of interbasin transfers. As you can see, all the red arrows here, water slushing about from one place to the other. Some of it, as I say, is pumping over 500 to 1,500 meters. Other places are going through a tunnel. It's an 80-kilometer, 5-meter diameter tunnel, and another one here. So we've got some fairly serious infrastructure. It's all linked together into a model. Each river basin, each of these boxes is a complicated river basin in itself with a number of different reservoirs, demand centers, pumps, you name it. So it can get very, very complicated. This is what it looks like. I don't know if you can see the detail there, but let me go in a little bit. There we go. Okay, there's a dam, and it's got a demand center, an irrigation, penalty structures, area capacity information, you name it. This network is probably one of the most complicated river networks that's ever been put together. And it was put together by my colleague, Karen Siegel. She's an engineer with my company, and she prepared this network and has been running it for the last couple of years. Not all our engineers look like Karen, unfortunately, but we do our best. The system that's been put together incorporates 87 large dams, 279 small dams. Some of these large dams, a couple of them are 200 meters high. You know, they're serious dams. They're part of the world big dam list of big dams, I suppose. We've got lots of abstraction points, integrated subsystems, 4,000 channels. We've got over 300 naturalized streamflow files. A couple of pictures, just to show you what the dams look like. Just some of the dams, just so that you know I'm not kidding about them being real dams. This is one of the tunnels, the Orange Fish Tunnel. It was, I believe, when it was built, one of the longest water transfer tunnels in the world at the time. It's over 80 kilometers. It's about 50 miles long. Mohali Dam, Katse Dam is over 200 meters high. It's up in the Lesotho Highlands. This tunnel taking water from Katse Dam to Johannesburg is basically also about 80 kilometers long. Now, most of that water flows towards money, generally. And in the case of South Africa, most of the money is in the middle of the country, not at the coast. So the water is tending to flow inland towards the mines, the power stations, and the big cities, Johannesburg, Pretoria, those types of cities. We've got about 10 very large open-cast coal mines, each of which has 5 or 6 of these. It's a drag line. It's an American-built drag line. Each of these is over $100 million. And this mine's got 6 of them. And we've got 10 or 12 mines like this. So they're quite big mines. We've got the world's largest platinum deposits. I'm giving you a few of the big things that we've got just to get you fired up here. We've got the deepest gold mines in the world. They go down 4.5 kilometers. That's down to level 134. So it's something like 13,400 feet deep. We've got one of the world's, if not the world's largest synthetic fuel plant. It is also, they don't advertise this too much, it's also the world's largest point source of carbon dioxide. So, but it's a very environmentally conscious company. They're very good. And they are actually, I'm not joking on that one, they are doing a great job. I think they're also in America. The company's Sasol. They use the Fischer-Tropsch process, which was developed by Germany during the Second World War to convert coal to fuel. And they produce 30% of South Africa's fuel directly from coal at this plant. We generate 50% of the power in Africa at about 12 thermal power stations when they're working. We're having a bit of trouble at the moment. We've got a lack of power at the moment, so we do have some shutdowns now and again at the moment, which is inconvenient. Something you don't know, or maybe you do, I don't know. There's a lot of arms people here, sort of defense. You may know about this, but South Africa's got a nuclear facility just outside the capital city of Pretoria, and we had enough enriched uranium for 12 nuclear warheads, and when they decommissioned the plant, 6 of them had already been prepared into, they had the bomb, basically nuclear bombs. South Africa is the only country in the world that has developed nuclear weapons and voluntarily got rid of them themselves. So I wasn't involved, but it was back in 1989, so it wasn't too long ago. So before the previous government handed over the keys to the cupboards of the new government, the ANC government, they cleaned out the nuclear cupboard quite significantly and passed it over. I think America and Israel got most of the gear, as far as I'm aware. Okay, naturalization of hydrology. When we analyze a water system, and I'm going through a few sort of technical things on hydrology here. I've tried to make it nice and easy. We normally find, if you look at a stream flow record, typically the stream flow record over time will decrease. The annual runoff from the river will decrease. A lot of times it's not due to climate change. In many cases, I'm not saying all cases, but in most cases that we deal with, this natural dropping off of the runoff is due to increasing afforestation, increasing land use, irrigation demands, or other interbasin transfers, or industrial demands, or municipal demands. So this hydrology here is not static. You have to adjust it and add back the impacts of land use change in order to get what we call a naturalized hydrology. And that is the basis for our system models. We start with the natural hydrology by adding on all the interbasin, all the developments that have impacted upon the river flow. What we then do is we take that natural hydrology and then we subtract all the developments again from the hydrology. Only this time we're subtracting them at current day development levels. Okay? So they're not growing now. They're now static at today's development levels. And we end up with a hydrology record, which is a synthetic record of sorts, but it represents the water that would have flown in the river had today's development's been there from the start. And that's quite important. Let me just go on to this side. Okay, so this is quite important. And the reason it's important is if you look at drought events, typically most of the serious droughts that you see in the world, they're all happening now. They're happening at the end of the record. No one looks back at the 1929, 1930 drought because it didn't cause any problems. It wasn't severe because there weren't any developments. So what we're doing by naturalizing the hydrology and taking off the developments at the current level, we can actually go back, and we sometimes find that the drought of 1930 is more severe than the drought of 1983. And that's one of the key elements in the naturalization and use of hydrology in the models that we're doing. Stochastics, I've mentioned stochastic yield. What is it and why do we bother? One of the reasons we bother is if you look at a hydrological record and you analyze the yield of that hydrological record, if you have a short record, 1930, say a 5-year record, for argument's sake, we get a yield of 81. If I add on another 5 years and it's a 10-year record, that yield now drops to 69. If it's a 20-year record, it stays the same. 60-year record, it drops to 36. Which one's correct? They're all correct for the record length. But it doesn't tell. You've got to bear in mind, hydrological records, it's equivalent. If you think of it like a chain, you're adding links to a chain. And the strength of that chain is always the weakest link. So if you add links on at the end that are stronger than the previous weakest link, it has no impact. If you add a link on at the end that is weaker, you will reduce the yield. So by extending the length of the hydrology, your yield either stays the same or it goes down. And what that's telling you is the longer your record, the more chance you've got of having that 1 in 100 or 1 in 200 year failure. And that's quite an important point. In South Africa, our hydrological records were generally only about 30 years long. So we use a rainfall runoff model in order to extend them up to about 100 years. A rainfall runoff model would be similar to, I don't know if any of you have ever heard of the Stanford watershed model. That was the first rainfall runoff model ever developed here in America at Stanford University. That model, we've got similar types of models to that we use in South Africa. Every country's got its own preference. Doesn't really matter. What we do for every one of the 400 reservoirs or dams in the system, we generate 1,000 plausible inflow sequences, and we model the impact at each reservoir in the system model. And we end up with a whole mess, really, for want of a better word, showing you what the storage within the reservoir could do. We then add a probabilistic thing to it, it's a technical term for probabilistic things. And what that does is it's got the minimum and maximum, and where the red and the blue join is your most likely scenario. So you're predicting some sequences that are above, and you're predicting some sequences below, which is obvious. I mean, the highest one, it's full, it's spilling. You could have guessed that one. The bottom one, this is your worst case scenario. But this is what you would expect that reservoir to do over the next 12-month period. This is a very simple example. We normally do 10, 12 years at a time, and we normally work with a moving window. Every 6 months or every year, we update the storage, the starting storage, and then we try and predict what's likely to happen. And you end up with this type of diagram at every single reservoir in the country. And it gives us an indication of what we expect to happen over the next 5 or 6 years. And it gives you the odds, the probabilistic odds of things happening or not happening. This is a real example for the valve system, which is our main system. Those are the curtailment levels. If the reservoir level gets to any of these bobbles there, then we implement restrictions. For example, here, this is the annual pattern. You can see here, we had a very bad year here, where it should have gone up, but for some reason we hit a drought, and it just kept tanking. This could be what's happening in California just now. You could be on that slope. You could be way down. Actually, you might be much worse. Once it gets to this point, you implement restrictions. Okay? And in this particular case, we implemented restrictions, and it continued to go down for 6 months, and we were starting to panic, because it's now moved down to, it's getting close to our worst case scenario. Not quite, but it's starting to creep down there. As luck would have it, we had the mother of all floods, and all the dams filled, people got washed away, and everyone forgot about the drought, and it was all happy after that. So that went well after that. That was good. Climate change. Okay. You've seen this before. I'm not a climate change denialist. I do agree that climate is changing. However, I've analyzed 5, 6, probably thousands of rainfall records in South Africa. And the mass plot on the rainfall records suggests that there is no noticeable difference in the long-term rainfall average in South Africa as far as the annual totals are concerned. And we've analyzed thousands of rainfall records, thousands of them. And it's just a simple mass plot. If the average was going up or coming down, this curve here would either be creeping up that way or creeping down that way. Straight as an arrow as far as rainfall goes. I'm not denying that the temperature's increasing. I think that's, everybody knows it's happening. What I'm saying is, I agree that there's climate change. What I cannot do is I cannot predict the impact of the climate change on my water resource system. That's my problem. I can't, with any level of statistical certainty, we cannot use it as a predictor. Every time we look at climate change, people go, well, what if it drops 10%? It's scenario-based. It's always, if it goes up 10% or it goes down 10%. We even employed the top team in Germany from, I've forgotten the name of the university in Germany. It was one of their top, they've got a huge computer. It's the size of this room. It would probably fit in an iPhone now, but in those days, this is a couple of years ago, and they analyzed the Orange River Basin, which is the biggest basin in South Africa, and their conclusion was that the temperature's going to increase. There's no doubt, 100% certainty, temperature's going to increase. The rainfall over the Orange River Basin might increase, or it might decrease. Now, we paid $1 million for that. Okay, so I don't know. What do we do about climate? Anyway, the nice thing about the system analysis is that the sequences that we're generating using system analysis are well above any potential impacts of climate change. And they give us sequences that are both above and below anything likely to happen due to climate change. So that's the South African situation. A lot of climate, it's a nice thing to, you can use it if all hell breaks loose and you don't know what's quite going on. Climate change is an easy thing to blame. You know, you don't fire anyone over climate change, but we are managing our systems using a stochastic approach, and it's a very, very powerful tool. How long have we got? Good. You can't talk about water resources without talking about leakage. And when it comes to leakage, I'm a member of the International Water Association leakage group. And one of the things we do there is we have an indicator called the Infrastructure Leakage Index. I had to throw in an acronym or two just to keep up with Professor Bosch, I think. And I wanted to show you this. This is ILI. It's basically an indicator where 1 is perfect, 2 means that your leakage is twice what it could be, 3 means it's 3 times what it could be. In the case of South Africa, for most of our systems, the average is about 6. But you're not that much better than us, actually. If you look North America, the average between Canada and the American data sets that we've got, your average is about 5. So you've got some room for improvement as well as ourselves. Places like Turkey, they're up at about, that's 5, 10, 50, they're up at about 50. India, some of the numbers are up at 300. Thailand, they're up at 300. So we're not doing, South Africa and North America are actually not that different when it comes to leakage. We operate our systems on high pressure. Most of our systems are operating at an average pressure of about 70 psi, or 50 meters. And some of them in Johannesburg go up to, we've measured 240 meters in one of our Johannesburg systems. Anyway, the equation that we use, you calculate an unavoidable annual real loss, so the UARL, I'll just talk, and it's 18 times the length of mains plus 0.8 times the number of connections. Okay, so it's a little equation here. I'm giving you the equation. You don't have to go on the internet. This is a simplified version that we use in South Africa. We eliminate the third term, so it's a fairly easy calculation. You use this to calculate the unavoidable real losses in liters per day for a system. You then compare it to what you've measured for that system, and you divide the two, and you get a ratio. And if the ratio is 1, then you're perfect. If the ratio is 10, then it means that your leakage is 10 times what it could be. You've got scope to improve. Okay, it's a bit simple. So for most clients, they like more complicated equations. So we sometimes use that one. And in Europe, we use this one. And for America, we've got this one. Okay, another indicator that we use quite often is the ratio of spectators to workers. You can see this is quite a good, this is one of our better ones. This one's pretty bad, actually. This is changing the name of one of our roads. It's a very important job to be done, and it requires a lot of skill and attention, as you can see, and moral support. This is a pipe with a leak. This is a leaking pipe. You can see this little pipe here. I just wanted to touch on that one. This ran at 25 cubic meters an hour for 3 years. Okay? Which is it lost over that time, I think I've calculated it correctly, I think it's 264 American gallons to a cubic meter or something. It's about 160 million gallons it lost. I've brought it with me just to show you. Here it is. I brought a prop. So there it is. It's a leaking pipe. And it cost, that one cost about, how many millions of dollars? It was a lot of money. It was a huge amount. After we fixed the pipe, that was the logging result that we got. So you can see the difference. This is it before, so way up here. That's all leakage. This bit under the curve there, that is all leakage. This one little leaking pipe, that little tiny thing here, lost 600,000 cubic meters of water, typically at 10 Rand a cubic meter, say $1 a cubic meter. $600,000 worth of water through that one leak. Another one, smart metering. We're coming to the end, we're getting there. They have something called smart metering, where you get the daily total of the daily amount of water going through a water meter. We've developed our own software where we monitor. We've got about 4,000 users on our system, where we're monitoring the flow and or pressure going into an area or a factory or something. In this particular case, this is the water going into a factory somewhere in Africa. I don't mention names, we keep it anonymous. And it's not Nokia, by the way, just in case you're wondering. Or Ericsson, it's neither of those two. So basically, they were running about 1,000 cubic meters per day. And the client was quite happy because it was relatively consistent. There were no big alarm bells jumping out. It's been like this for 5 years. When we put our loggers on and we started using our own software, this is what we found. This is the logging result over a period of 2 or 3 days. And what it's showing is that you've got a base flow here, which is actually all leakage. And you've got some spikes here where people are filling a tanker. That could be somebody with an avocado farm, for example, that wants water. And they could just be filling a tanker, accidentally, obviously. And they're taking water in water tank. In this particular case, we think they're probably selling it to someone. But otherwise, it's being used somewhere for something. That's the tanker filling. Roughly $100,000 per year, tanker filling. Their actual use in this factory is $100,000 per annum. Their leakage was $1.1 million per annum. And that's showing you the three together. So that's the leakage. The orange is your normal use, and the red is the tanker filling. So it's quite a nice example. Final example I'd like to show you, pressure management. America's actually well advanced on pressure management. We have a leak here. It's a little leak running during peak demand period when the pressure's low. The same leak at night time when the pressure's high would look something like this at high pressure. So can you see the difference there? Low pressure, high pressure. Right? You've got to watch carefully. Okay, what we did in this case, we put in we built something. It was a big installation with green bits and blue bits. And we reduce the pressure at night time when everybody's asleep. Nobody knows that we've done anything. That's the trick. If people know you've done anything, they want to complain. It's just a natural, it's a human thing. If change needs a complaint. So we don't tell them what we're doing, and we reduce the pressure at night time when they're all asleep. The water going into the area is the red after, and before it was the yellow. So we dropped the average from 2,500 cubes an hour down to about 1,500 cubes per hour. We had an annual saving of 9 million cubic meters of water on that installation. That is saving an hourly saving of an Olympic-sized swimming pool every 2 hours, or a big reservoir every year. So although you can't ignore the actual network side, the losses due to leakage can be astronomical. That installation had a payback of 6 weeks. And I've got a couple of quotes. I got a real one this time. Whether you think you can or you can't, you're usually right. It's a Henry Ford quote. This is one of my favorite ones. And just, I don't know if Prof. Bosch is here. I've got a slide for Prof at the end here. This is our one. I'd like to finish on that. Thank you.